My name is Andrei Belenko. I am a chief security researcher at Telkomsoft, and today I would like to talk about iOS data protection, and more specifically about the implications this technology had on iPhone forensics. So, I will start by giving a short overview of the iPhone forensic techniques, then we'll move on to the pre-iOS 4 forensics. We'll talk a little bit about iOS 3 forensics and how that worked. We'll then describe an iOS 4 data protection technologies in more detail and move on to the iOS 4 forensics and how this can be accomplished with respect to the data protection. When it comes to computer forensics, there are traditionally three steps. The first one is acquisition, the second one is analysis, and the third one is reporting. And we will talk mostly about acquisition today. The goal of the acquisition is to acquire as much information from the device as possible. It doesn't matter what the device is it a computer or mobile device or something else. And we also would like to leave as little traces on the device as possible to make the evidence, like forensically, to be usable in court. So when it comes to iPhone forensics, there are traditionally two general ways of doing the acquisition. The first one is to utilize the built-in function of the iOS to ask the device to create a backup of itself. And this method is very good in the sense that it's very non-invasive. So it doesn't alter the device, so the device contents are not changed. It doesn't require any sort of hacking of the device. The downsides, however, are that the amount of information which is available with this way is very limited, and the exact information which is included in the backup depends on the particular version of the iOS the device is running, and it can be changed. For example, Apple can easily change the amount of information which is included in the backup in the upcoming iOS 5, for example. The second problem with the backup approach is that if the device is passcode protected, it will not create a backup. You just cannot ask the device if it's locked to create the backup. You need to unlock the device first. You have to know the passcode, or you have to get the so-called escrow keys from the computer. I will talk about this later. And the third major problem is that iOS device can be configured in such a way that it will produce encrypted backups. So you ask the device to create a backup of itself, it gives you an encrypted backup, and after that you need to run a password cracking attack on this backup, and this may be successful or it may not, so it depends. So the second general approach is to utilize some sort of boot time exploit to load custom RAM disk and custom kernel on the device and perform the physical or logical acquisition. The difference between physical and logical here is that physical acquisition obtains a raw disk image, so it's like running a DD on the iPhone. Basically, it is running the DD on the iPhone. And the logical acquisition is just obtaining individual files, some of them or all of them, from the device file system. So that's the difference. The obvious benefit here is that this approach can get you all information which is stored on the device. Passcode is generally not a problem for the acquisition itself, although it may be a problem for the later analysis stage. Again, I will talk about this a little later. The problems, there are two downsides. The first, that we need a boot ROM exploit, boot time exploit, which is, well, it limits the scope of this attack. For example, at this time there is no boot time exploit, public boot time exploit for an iPad 2. So this device is currently cannot be acquired like physical acquisition. And the second problem is that raw images which we can acquire with this method can be encrypted. And actually this is the motivation behind our research, because the initial physical dumps of the iPhone 4s, when it came out, showed that the raw images of the disk, they are quite strange. They have the the file system structures in plain text, so you can see the files, the directory tree, and all these kind of things. But when you try to read the file contents, they're encrypted. So that's it. There are three major aspects of the forensics of the iPhone security when it comes to forensics. They are storage encryption, keychain encryption, and passcode protection. So in iOS 3, it was pretty easy, all of these parts, and I will start with this storage encryption. Well, first of all, before iPhone 3GS, there were no hardware encryption, so the storage was not encrypted on the devices, no matter what version of the iOS they are running. For example, the iPhone 3G, even if it's running iOS 4, there is no storage encryption. On the compatible devices with the hardware encryption running iOS 3, the data was actually encrypted, but the encryption was there not to provide data confidentiality, but it was to ensure that fast wipe is possible. So the data was encrypted and decrypted by the device automatically and transparently to the application. So it created no problems for logical or physical acquisitions. The keychain is a system-wide storage for secrets like passwords. On iOS 3, all items in the keychain were encrypted using the same key. The key is known as SecurityTube key or key 835 hex. The problem with this approach is that this device key, SecurityTube key, is fixed is constant for the lifetime of the device. So, in fact, since all the keychain items were encrypted using this key, it meant that all past, current, and future keychain items for the given device, they can be decrypted if you manage to get this key. This is not a very good thing to do. And the layout of the keychain item is shown on the screen. There is a random IV and data encrypted payload which contains the data itself, usually the password, along with the digest for integrity checks and padding. Another thing with iOS 3 is that device passcode is, if set, it was stored in the keychain. So if you manage to read the keychain contents, you can just recover the passcode instantly. And there were no additional protections with regard to the passcode besides the lock screen. So it was very artificial. So the iOS 4 introduced the thing which is called data protection, which is a set of security measures to protect data at rest. So there, with regard to the mobile forensics, there were three new things: the storage encryption, the iTunes backup, and keychain encryption. Those things were different in iOS 4. Well, the iTunes backup was not a big deal for forensics because starting day 0, there was a proprietary tools to deal with that. For storage, there were no tools until recently. And as I have described, the file system encryption is not very typical. I mean that the file system metadata, the directory tree, and all these kind of things were decrypted. But the file contents were actually encrypted. So before I can describe the encryption of the keychain and the storage, I need to take a little detour and to explain some internals of the data protection on iOS 4. iOS 4 introduces a concept of so-called key bags. Key bag is a collection of encryption keys. And it also introduces the concept of content protection classes. iOS defines several content protection classes which correspond to three accessibility domains which are also defined for all the data which is stored on the device. So those accessibility domains are the data available only when the device is unlocked. The data is available only after the device was unlocked for the first time, and the data remains available until the device is switched off or reset. And the data is available at all times, no matter the device locked or unlocked. So there is a content protection class for all of these accessibility domains. There are separate protection classes for user files and for keychain items. And each protection class uses its own encryption key, which we will call the master key for this particular protection class. And each such master key is stored in the key bag, in the system key bag, in the scroll key bag, and it is protected with the device key, which is unique to the particular device, and optionally with the passcode key, which is unique to the passcode. So it depends on the passcode. And what's important that these key bags and content protection keys, they are regenerated, recreated every time you run the device restore. So if you just need to wipe the device, you can restore the device to default settings in the iTunes, and this will recreate all the content protection keys and all keys which possibly could have been compromised before. They will not be of any use with the new device. So the whole system looks pretty much like this. So there are two device keys. There is one hardware key, which is in red, which is UID key, which is embedded in hardware. And it is used to compute two device keys, the key SecurityTube key and key 890B. And there is a special area on the iOS devices which is called effaceable storage. Its purpose is to store small amounts of data which may require fast wipe. So this is the name, effaceable storage. And on iOS 4, it stores three encryption keys. So the first one is EMF key, which is a file system whitening key. It acts pretty much like a default encryption key for user data partition. All data which is not a file with a certain protection class is encrypted using this whitening key. So all the file system metadata and files for which no content protection class is explicitly set, those files are encrypted with whitening key. The second one is the bag1 key, which is an encryption key which is used to protect the payload of the system key bag file. The system key bag is stored on the file system, and its payload, its contents are encrypted with the bag1 key. And the third key is DK. It is actually class 4 protection key. It really belongs to the system key bag, and this is shown on the screen. And the reason it is stored in effaceable storage is because system key bag itself is stored in the file, and the file is encrypted on this D key, and you can't really store encryption key to decrypt the file in the file itself. This introduces some sort of conflict. You can't really decrypt it. So this is why it is stored in effaceable storage. So the ultimate secrets which are required to decrypt all data on the device, I mean data belonging to all content protection classes, is a complete set of unlocked content protection keys. And there are actually two ways to obtain them. As you can see here, the unlock requires that you provide two keys. The first one is device key, and the second one is passcode key. Well, the obtaining device key is relatively easy. Obtaining the system key bag in the locked state is also relatively easy, but obtaining the passcode key might be difficult. And it may require the passcode brute force because there is no simple way to just extract it from somewhere. In iOS 4, passcode recovery requires a device because the passcode transformation, the passcode key derivation function is tied to the hardware key, and you cannot run this outside of the device. And the problem with this is that passcode brute force is really slow. We have to do this on the device, so we can't really use any of these fancy GPUs or stuff. And the password recovery speed depends greatly on the device. For example, on the iPhone 3G, it is about 2 passcodes per second, and on an iPad, it's more like 7 passcodes per second. But there are still two things which make it possible to recover the passcode. The first one is the human factor. Nobody likes long passwords, maybe except of you guys. But pretty much everyone is using the simple passcode, which is 4 digits, or not using a passcode at all. And the second factor which helps is that system keyback actually stores the type of the passcode which is used to protect the device. Just by looking on the system keyback, you can tell with a 100% certainty that whether this particular user is using simple passcode or not. So, and if you have a confirmation that the passcode is simple, which is 4 digits, then you can easily spend like 10 or maybe 20 minutes and get a passcode just by brute forcing all possibilities. There are not too many of them, just 10,000. So, but if there is an alphanumeric password, then this is not an option. This can take like weeks or months, and usually during forensics there are no such time frames. So there's another option of obtaining the complete set of unlocked content protection keys, and this is the iOS 4 escrow keyback. Escrow keyback holds the same content protection keys as the system keyback. It is created by the iTunes the first time the device is connected to the computer in the unlocked state. The keyback itself is stored on the computer, on the PC or on Mac, and it is protected with a random 256-bit passcode, and the passcode is stored on the device. So there is a sort of, the keyback is stored on the computer and the passcode is stored on the device, and you still need the device to compute the escrow key to unlock this keyback. But if you have both the escrow keyback and the device, then you obviously don't need the passcode, and this is the good thing. So this was a sort of long introduction about the iOS 4 internals and iOS 4 data protection internals, and now we can move to the actual iOS 4 keychain and storage encryption. The keychain encryption provides 6 protection classes. They're parallel to the accessibility domains, accessible always, accessible after first unlock, and accessible only when unlocked. And it also provides 3 additional classes which are duplicates of those, but with this device-only suffix. And items with this suffix, they will not migrate to another device. So they're encrypted in a way that they cannot be decrypted on a different device other from the one created them. Each item is encrypted using a unique key. And this encryption key, which is specific to particular keychain item, is then protected with the master content protection key. And everything is stored in the keychain, which is a SQLite 3 database. So there is it's no longer possible to extract one key from the device and get the ability to decrypt keychain contents for life for this device. The storage encryption, there are 2 documented protection classes, the protection known, which is accessible always, and protection complete, which is accessible only when unlocked. And for example, built-in mail application on the iPhone 4 uses the NS protection complete to protect the email databases, so they are only accessible when device is unlocked. File system metadata and files without any protection class are encrypted using a whitening key. Each file is encrypted on random key, unique key, and this key is then protected with the content protection key, and this protected key is stored in the extended attribute of that file. Now, this is the problem which we faced with the raw images. When you obtain a raw image of the disk and try to decrypt the files, you will get garbage. They will not decrypt. The problem is that when you read the block device, everything gets decrypted on the whitening key. So actually, to decrypt the file, you need first to encrypt it using the whitening key, and only then decrypt with the unique file key. So this is pretty much it. I have just to sum things up. iOS for forensics, it's no longer enough to acquire raw disk image of the device. You need also to extract the encryption keys from the device. And also, you might want to extract the whitening key from the effaceable storage. Now, you can theoretically, there are two approaches. You can theoretically extract only the green items, which are the unlocked keys and the whitening key. But in real world, it might be way better to extract the source data. I mean, the device keys, the passcode key, and the effaceable storage. This will give you more flexibility if something is wrong with the device or with the keys or something is damaged. So you can rerun the process of computing the keys and all these kind of things. And to conclude, with this research, the iPhone physical analysis is possible again. The problem is that such physical acquisition requires boot time exploit. Passcode is usually not a problem, either because it's not set, it's simple, or the scroll keys are available. And it's also worth mentioning that there are proprietary and open source tools are available, and there are independent research group at Sugeti who actually gave a very similar presentation somewhere in between our submission to BlackHat and the BlackHat. And they did all this research independently, and they actually maintain the open source repository for the same tools, and we provide proprietary tools. And thank you very much. Please turn in your completed feedback forms at the registration desks, and if you have any questions, if you want, we can run the questions? Okay. If you have any questions, you can ask them now. We have 5 minutes. Yep. Yes, I am. You can look at my title.
Sorry.
No problem. Actually, I'm one of the developers of this toolkit. So if you have any questions. Oh, if anyone wants to see a demo, we will be available until end of BlackHat and for DEF CON. So just find us. And thank you very much.